Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at National College of Ireland. I hope you are all doing well. I can see, I think there's about 11 people live now. I'm just going to type a message here just in the message box. And the message is just, I suppose, oh, better lower that down, that's very loud. Okay. And I suppose the message is just really going to ask whether you can hear me. Okay. So can you hear, uh, can you hear uh, the vocal, yeah, okay, or the audio, let's say. Okay, can you hear the audio? Okay, yes, brilliant, Beatrice, that's great. Okay, good to hear. Uh, Everybody else is 12 other people there. Brilliant. Yes, yes. Mark Fallon. Hi, Mark. That's brilliant. Okay, great stuff. Okay, seems like everything seems to be going well there from an audio perspective. So I haven't really done many of these live streams, so maybe if you can have patience with me. Uh, Maybe for the NCI students, I suppose what I have been asked to do is I am aware that you have a class test coming up for the higher diploma in data analytics and in particular the business data analysis module. Uh, and this is on the 25th of October. So you have a sample paper here, and I've actually been asked to run through this particular sample paper in relation to what's going on with all of the questions. So I suppose that's really what I'm going to do today, and I hope that's all right. So maybe what I should do is I probably should really get started. No, I am conscious. I have a screen here, a light box, yeah, that's being recorded by a camera, and it's also recording my audio. So I will put this up online so that you can actually reflect back over it. But I am conscious that at times maybe I do talk a little bit fast. Uh, and I do have the chat window over the other side in the corner of my eye. So I'm going to try to keep an eye on the chat window as well in relation to any questions. You probably can't really see this, and hopefully you've got a copy of this yourself in front of you. Uh, and well, you can see the camera here. Hopefully you can actually see my screen. I guess has a reversed, yeah. So question one it has here, part A, says distinguish between what is meant by a one-tail test and a two-tail test. Illustrate your answer with an example not already used in class. So let's just have a look at question one. Okay, so this is question one, and it's part A. Okay, and really what we have to do is we have to try to get across our understanding of a one-tail and a two-tail test. Okay. Uh, well, okay. So there's basically three types of hypotheses that we can actually undertake when we do a hypothesis test. Okay, albeit they're all a hypothesis, but there's actually effectively three types that we can do. And let's say the first one here has a null position and has an alternative position. Let's say the next one has a null and has an alternative, and then the third type it has a null and has an alternative associated with. And let's say, just for argument's sake, now I am conscious that there's a question later on that talks about body temperature, okay, and asks us to test something in relation to body temperature. But let's say, for argument's sake, I want to test whether there's evidence to suggest that the average grade of students, yeah, okay, that the average grade of students on a maths exam, is there evidence to suggest that the average grade of students on a maths exam is greater than, let's say, 60%, okay? So I want to find evidence for that. So the average is the mean. So the symbol I have for that is mu. And I'm just going to jump to, I'm just actually going to write that over here. Okay. So I'm going to say, and I'm going to do it as the alternative. So mu greater than 60%. This is the research question that I have. The question that I'm asking is there evidence to suggest that the average grade of students on some maths exam is greater than 60%? Okay. So that's one way I could ask the question. Okay, I could also ask the question. Well, I'm not interested in whether there's evidence to suggest that they're greater than 60%. Maybe another question might be: is there evidence to suggest that the average grade of students, let's say for argument's sake, is less than 60%? Okay, or 40% or whatever value. Let's just use 60%. Okay, that's another question we could ask. Okay, see, the alternative is the only place that we can ever move to based on our evidence. We always assume the null to be true. The null is always assumed to be true. And when we find the evidence, we hope that we move away from the null position towards the alternative based on the evidence. Right? So now I have two tests. I could ask the question, is there evidence to suggest that the average performance is greater than 60? I could also ask, is there evidence to suggest that the average performance is less than 60? Okay? And there are two types of questions I can ask. But I could bring these questions together and I could say, is there evidence to suggest that the average performance is greater than 60 or less than 60, if that makes sense? Yeah. So if something is greater than 60 or less than 60, well, then that means it's actually different to 60. So this null in here, this alternative in here, is that the average performance is different to 60. Okay, if that makes sense. Which gives us then all of our null positions. Don't forget, these averages are on a continuum. These averages have to appear somewhere. Here's infinity, here's minus infinity. We're talking about continuous variables. These averages have to appear somewhere along here. So if this position here is that the average is greater than 60, let's say here, greater than 60 means its values over here. Well, then the where we're going to start from is to assume that the actual average isn't over there and it's actually down in this direction over this particular side. So the full continuum has to be captured with respect to a hypothesis. Okay, so the full continuum captured here would be that the null would be, let's assume it's less than or equal to 60. Okay, so we're going to assume this to be true, that the average is less than or equal to 60. And if we find evidence against that, well, then we'll move away and we'll say that it must be greater than 60. And then over here, well, the other part of the continuum that hasn't been captured here is that mu is greater than or equal to 60. And in this situation, the only thing that hasn't been captured is the point when mu is equal to 60. Okay, when mu is equal to 60. But really what I want to try to show you here is that there's actually a distribution. Okay, so under the null position, okay, under the null position, which we assume to be true, we assume h0 to be true. Now that doesn't make it true, it's just an assumption. Okay, under the null position, the distribution is positioned somewhere. Okay, and actually under the null position, where the distribution is positioned is, well, it's positioned at 60 or any value. In this case here, the null distribution, these mean values that we're assuming to be true, that the average grade is actually greater than or equal to 60. So the average grade could be at 60 or anywhere greater than it. Okay, so this is like a demarcation point for the average. But don't forget, the distribution itself has a standard deviation. Okay, to arrive at the mean, the average, we must have values that are less than that and values that are greater than that. So actually, this null distribution, okay, has a standard deviation. So this is our null distribution. This is our h0 distribution here. Okay, if that makes sense. Yeah. Now, for me to show that the actual average grade is less than 60, I need to find evidence over in this particular direction over here, because that's where the values are that are less than 60. Okay, so I need to find things over here, or effectively, if you look at the arrow, okay, the arrow is like this in here. I need to find things in the left tail. Okay, if I find evidence in the left tail out here somewhere, okay, well then that's evidence to suggest that the average is less than 60. Okay? And that's why we call this a one-tail test. And more importantly, because it's where you need to find your evidence is what determines whether it's a one-tailed or a two-tailed. So in this situation, this is actually a left-tail test. Okay? In this situation over here, the null distribution is positioned on 60. Here you go. And or less than or equal to 60. So the null distribution is it could be positioned, its measure center anywhere over this side. But it must be at least at 60. So, and it also has a standard deviation or a dispersion associated with it. So to show this to be the case, we need to show that the evidence, okay, is over here in the right tail, if that makes sense. Yeah. So for me to move away from this less than or equal to 60, the evidence has to be greater than 60. In other words, it has to be over here somewhere. It has to be so far away from here. It has to be in the improbable area associated with the distribution. And now you can see, so this is now another a one-tail test. Yeah, this is a right-tail test, because that's where we need to find our evidence. To move from here to here, the evidence needs to be in the right tail, because things in the right tail are greater than 60. And then when we bring these two things together, right, the distribution is positioned, the null distribution is at 60, but it has a dispersion. Okay, for me to show that this is the case, well, I don't mind finding things over here or finding things over here in either situation. And if it's far enough away, and that far enough away is determined by the significance of the test. Okay, if it's far enough away, well, then we'll be able to move from here to here, if that makes sense. And this is, you can see, I don't mind being over here, or I don't mind being over here. So this is what's known as a two-tailed. This is the two-tailed test. Okay, guys, I have 21 of yous there now. As I said, this is all being recorded. That question here, question 1 part A, said distinguish between what is meant by a one-tail test and a two-tail test. Illustrate your answer with an example not already used in class. I know I'm not sitting in your class, yeah, so I don't know whether this example in relation to average maths grades are going to do. It doesn't make any difference. The test might be, let's say that the average time it takes to run 100 meters, yeah, by a particular class of students or a particular population of students is greater than 60 seconds, is less than 60 seconds, or it's not equal to 60 seconds. You can change these things, just change the scenarios. Once the variable is a continuous variable that we're measuring, if that makes sense. Yeah. So, guys, I'll just maybe just ask the question now. Is there any is there anything that I need to cover, yeah, in relation to in relation to what's going on here? Or has this helped with our understanding of what a one-tailed and a two-tailed test is? Yeah, maybe I'll just ask that question there out to you guys. So there's about 20 views online now. Yeah. So has this helped in our understanding of what a one-tailed and a two-tailed test is? Okay? And let's keep in mind that this is a single sample test here. Okay. This is a single sample test, and the parameter that we're testing is mu. The parameter doesn't have to be mu. The parameter could be anything at all. I mean, I could test whether, let's say, whether the variance, okay, is equal to 60, or whether whether the variance is not equal to 60. So it doesn't have to be. So the parameter now is the population variance. Yeah, the parameter here is testing the population mean. It could be rho. It could be the correlation coefficient. Yeah, is equal to 0, or the correlation coefficient is not equal to 0. The population correlation coefficient. Okay, it could be anything like that. It could be a coefficient on a regression model. It could be that the beta value, beta 0 is equal to 0, or beta 0 is not equal to 0. That's our null and our alternative. So it's basically the parameter of the population that feeds in here. But these are all still single sample tests. Okay, so the point being, it doesn't have to be the mean value. It can be anything at all. Okay, any population parameter that you want to test to see whether it's greater than, less than, or not equal to a specific value. Okay, guys, I think I'll move away from this now. Everybody looked good there in relation to the question. Oh, sorry, here's a question from Katie. So do you still have to still define the one and two tail test when answering this question? I think I think the question is just asking us what is our understanding of what a one-tail and a two-tail test is. Yeah. Okay. So the understanding I think should be, yeah, okay, is that the one-tail test, yeah, okay, is asking you. It's a test where the evidence needs to be found. Yeah. Okay. Hey, let me just get another colored marker. Yeah. Okay. So for us to reject, yeah, for us to move away from the null to the alternative here, yeah, we need to find evidence that's bigger than 60. In other words, we need to find evidence over here, okay? Not over here, not over here, over here, because these are the things that are bigger than 60, okay? So where we need to be is in one of the tails, not both of the tails, it's in one of the tails to reject. So that's a one-tail test. Similarly over here, for us to show that the average is less than 60, we need to find evidence that's over here, right? Not over here, over here, in one of the tails. So that's a one-tail test. For me to show that the don't forget, it's the alternative that we're always trying to prove, yeah, or find evidence in support of, yeah. So for me to show that the average is different to 60, I don't mind showing that it's over here or it's over here in either of the tails, in either of the two tails, and that's what gives us a two-tailed. So that's the definition of what a two-tailed test is. If you want a specific example, well, the specific example is the example that I've been using here. Is in this test here, the test is the alternative. This test is testing whether the average performance of students is less than 60%. This test over here is testing whether the average performance of students is greater than 60%. And this test is testing whether the average performance of students is different to 60%. So I suppose, Katie, the examples that you need to provide are real world examples, yeah, okay, not the abstract concept that I'm saying being in one tail or the other tail, but real world example, like maybe the average performance of students on an English exam, yeah, is bigger than a specific value or less than a specific value or not equal to a specific value. Okay? So Katie, I hope that answers that particular question. Okay? I can also take questions. Maybe I'll just provide my email address here, Jonathan Lambert, okay, at where am I going to at ncirl.ie. There's my email address if someone wants to follow up with a specific question. Yeah, later on, maybe after this session. Okay, so I'm going to just get rid of this page now, and I'm going to have a look at the next question. Okay, which is part B. Okay, and I don't know whether you can see this here, okay, but basically what we have is we have a data set, okay, we have 63 observations of body temperatures, okay. Uh, we have what's meant to be a histogram. Don't forget, a histogram shouldn't have any gaps between the bars. So technically, this is actually a bar chart. Yeah. Okay. But I mean, you could go into Excel. This was produced in Excel. You could go into Excel and you could double click on them bars and you could reduce the width, the gap between bars down to 0. Then you have technically a histogram because it should be a continuous curve. Yeah. Okay. So, but anyway, this is the histogram here. This is the histogram of bodies of this set of data of these 63 observations. And then what we have here is the output from the data analysis tool pack, the Excel data analysis tool pack, and the typical output that's produced. And we have the typical measures: the mean, the standard error, the median, the mode, the standard deviation, variance, kurtosis, skewness, range, min, max, sum, and count. These are numerical measures, yeah, okay, describing this distribution, where this is a graphical, this histogram here is a graphical representation of this distribution of values here. But anyway, the question that's been asked is to interpret and comment on this data and the output generated in Excel. Okay, so it's probably going to be, I don't know whether you can see this here, and I probably should have blown this up a little bit bigger. Yeah, okay. But anyway, when I look at the distribution itself, okay, maybe I'll just get a red marker here. Okay. I mean, when I have a set of data, okay, and when I produce, let's say, the descriptive statistics, yeah, the usual story that you're going to tell, yeah, in relation to trying to understand the data is to start on the extremities, okay, it's to start on the extremities of the data set and work in. So actually, what we can actually see here is that in relation to the 63 women, okay, so of the 63 observations, okay, of body temperature, body temperature, temperature. Okay, what we notice is this: is that I suppose, let's say, uh, the smallest temperature, okay, or the minimum temperature, okay, is here. So the minimum temperature, okay, is a temperature of 96.4 degrees, and these are degrees Fahrenheit. Okay, so this is probably a little bit more tricky for us in Ireland, yeah, okay, than when we use degrees Celsius. And actually, to be honest with you, I actually had to go on and do a conversion to actually see what that, not what that represents, but actually what 98.6 degrees Fahrenheit is actually 37 degrees Celsius. Okay, 37 degrees Celsius is the average body temperature of a human. Okay, so you can actually see that the minimum body temperature was actually below the average body temperature of the population of people in the world, if that makes sense. Which is typically set at 37 degrees Celsius. So what we know here is that there's some people in the 63 from the 63 women that have a temperature that's less than the average. Yeah, the average, let's say, of the average noted body temperature for people. Yeah, and the maximum temperature, okay, it goes up to 99.9 degrees Fahrenheit. Okay, so what we're really saying here is that when we have the min is at 96.4, the max is at 99.9, and everyone else, okay, is found between the min and the max, and that's all the min and the max allow us to, I suppose, let's say, identify. Yeah, is that dispersion? Yeah, okay, is that range, or is the demarcation points for the range of the data set? Now, the range of the data set, the range is the largest value minus the smallest. Okay, and in this case here we have 99.9 minus 96.4, and when we do that there, we have 99.9 minus 96.4, and that gives us a value of 3.5. So the distance here is 3.5 degrees Fahrenheit. Yeah, so what we now know is this: is that the distance between the woman with the smallest or the least body temperature and the maximum body temperature, there's 3.5 degrees between them. Yeah. So now they're the greatest, they have the largest distance. So no other two people selected from this group will have a difference greater than 3.5 because these are the two extremities of the data set, if that makes sense. And that's what the range allows us to understand or to interpret. And you can actually see in the data set here, it has that the range is 3.5. Okay. But really, what's interesting here, I suppose, for us is when we look at the more, let's say, the more important distributional shape parameters. So let's say the distributional shape parameters. Okay, I'll call them that, right? Okay, parameters. Now, albeit this looks like it's a sample of 63 women, so actually technically they're statistics. But these shape parameters are the mean. Okay, the mean. Uh, let's say we have our median, we have our mode. Okay, we have our standard deviation. We have our variance, which is just the square of the standard deviation, and we have our kurtosis. Right? And we also have our skewness. These things together, this is like if you're going to buy a dress, okay? And there's so many different types of dresses, yeah? You're going to buy a dress for your partner, okay? And there's so many different types of dresses and they have different shapes. I mean, there's dresses that are very slim. There's dresses that have, let's say, they're like ball gowns, okay? There's dresses that have long tails and so on. So these are the shape parameters, yeah, for the dress or for the distribution, if that makes sense. And what we have is this, is that we have, now we already know, okay, that the average body temperature ranges between 96, okay, down here somewhere, 96.4 and 99.9. But what we also know is that the actual average body temperature of these 63 women, the average, the mean is recorded at 98.33, okay? So it's 98.33. And if you think about that, yeah, how close? So we have 98.33 would be another 2 units onto this here, okay? So 3 units to get us to 99, yeah, or 3.5 units to get us to 99. So 2 units on. So it's actually further away from 96. 98 is. So what we actually now have is that the mean of our distribution seems to be down here. So this is the mean. The mean of the distribution seems to be positioned at 98.33 in around there, if that makes sense. And that's the center of the distribution. Okay, so that's the main body mass, if that makes sense, for the distribution is right there. Okay. Now, what we also notice is that the median is at 98.4, the mode is at 98.8. Okay, so we have now the median is at 98.4. So the median is right here. It's very close to that. Okay, there's the median. Okay, median. Okay. And the mode is at 98.8. The mode means that the peak is the highest part of the peak. So 98.8 is probably, well, let's say that's probably 1.5. So 98.8. So we have 0.5. So that's 1.5. So it's probably around here, if that makes sense. Yeah. So this will be the mode. I'd say it'll be around here. And that should be the highest part of the curve, yeah, because that's the modal observation where there's most things, yeah. And this is the least part here. So actually, you can even see here, just looking at it from this perspective, yeah, okay. So we have these demarcation points, and we have this growth, yeah. The curve is actually going to grow, okay, until it reaches its peak here, and then it's going to drop back down here. And this is what I'm just getting from the numerical perspective, if that makes sense, yeah. And you can actually see that this curve actually looks quite similar to the distribution that's being presented here, okay, if that makes sense, yeah. And that's my understanding. So actually, these numerical values always allow us to build this particular picture of the distribution itself, yeah, okay. But more importantly, yeah, now this is only a rule, okay, is the relationship between the mean and the median, okay, and the mode, yeah, okay. So the mean, the median, and the mode for a normal distribution, okay, for a symmetric distribution. If the distribution is symmetric, well, then we have that the mean, the median, and the mode, yeah, the mean equals the median and equals the mode, okay. Now, the other thing is this, and you can see that in this situation that there's a little bit of a difference between them. Yeah, so the the median value is 98.4. It's 98.4. The modal value is 98.8. So they're not actually equal. They're not equal to each other. Okay, but they're very, very close to each other. Yeah. Okay, but they're not equal to each other. That's the main thing to keep in mind here. Okay, so the distribution is not symmetrical, and I'm getting that from these three values not being equal. There's evidence to suggest that the distribution is not symmetrical. And more importantly, what we can actually see is this: is that the mean the mean value is actually less than the median, okay? Okay? And which is actually less than the mode as well. But now the mean value, the main thing here is that the mean value is less than the median, yeah, which now tells us the direction of the skewness, yeah, and the skewness is in that direction here. It's out to the left, yeah. So actually, this distribution is left. It's negatively skewed, negatively skewed, which actually agrees, and that agrees with the skewness value here, which is minus 0.61. Okay, so the skewness is minus 0.61. So it's relatively negatively skewed. It's not excessively skewed, but it's relatively skewed here. Now the question is, what's excessive and what's not excessive? Well, there's lots of things that need to be taken into consideration in actually doing that particular test. Actually, we'd need to do a hypothesis test to test whether SK, the skewness, is actually significantly different to zero, and more importantly, whether it's significantly less than zero, to actually find out whether we've got confidence to suggest that the skewness is actually negative. There's a hypothesis test that can come into play as well. Right? The one thing that I'm missing here is just the kurtosis. The kurtosis value, these are all giving us an idea of the shape. The kurtosis is 0.90. Okay, so what the hell does that mean? Now, the Excel toolkit itself, the Excel data analysis toolkit, I suppose reports a kurtosis, yeah, okay? Reports. So the Excel data analysis toolkit, okay, reports kurtosis uh, of a standard normal distribution, of a normal curve, of a normal distribution, okay, as zero, okay. Actually, that's a mathematical modification. The actual kurtosis is actually 3, okay, for a standard normal curve, and anything less than 3 is, I suppose, is platykurtotic. Anything greater than 3 is leptokurtotic, and if it's equal to 3, it's actually meso. It's normal, if that makes sense. But anyway, let's just keep in mind here. So there's a little bit of ambiguity here in relation to different, let's say, systems given different numbers. For Excel, the kurtosis is, see, in Excel they take 3 away from the actual kurtosis value to actually standardize things on 0. So in Excel we're compared into 0. What does it mean? It's a bit unusual. So the standard normal curve is there in black. Okay. A curve that's flatter, okay, that's flatter, means that what's at the happening is it's flatter, so it's at the pushing stuff out into the tails. So the tails are actually heavier, if that makes sense, yeah, okay, because it's pushed more stuff into the tails, okay. So this would be, the blue would be your kurtosis, a kurtosis that's less than 0, it's platykurtotic. The black would be your kurtosis that's equal to 0, it's normal, okay. And then we have, I suppose, really light tails. Okay, see, the body of the distribution has been pulled up in this direction up here. Okay, if I'm not mistaken. Okay, so what we now have is this is kurtosis value, a kurtosis value here of greater than 0. When we're taking the Excel data analysis tool pack as our way of understanding the distribution, and if we look at what we have 0.90. So what this is saying here in relation to this curve is that this curve is more peaked compared to a normal distribution. Yeah, it's peaked above this black particular line. Yeah. Okay? So with all of these things, with the mean, the median, the mode, the standard deviation. Well, actually, we didn't define the standard deviation here. The standard deviation is about 0.665. So that's 0.65 is the standard deviation. Which, if it was normal, we have the empirical rule. So I'm really doing a lot of work on this particular question here. Yeah. Okay. So our standard deviation, the standard dev, okay, which is, let's say, S for this particular sample of data here, okay, is 0.65. Yeah, it's 0.66 when I round it, if I'm not mistaken. When I round it to 2 decimals. Okay, what does that mean? Well, it means this now, yeah, that if it was normal, now we know it's negatively skewed, yeah, okay, we know that some of the stuff that, that there's less observations in the left tail, yeah, compared to the right tail. But if it was normal, we now know, and we know the mean value, the mean is 98.33. So now we know that within one standard deviation, okay, that's 98.33 plus 0.66. And 98 98.33 minus 0.66. Okay, that gives us values here. That gives us 98.99. And over here, that gives us, what does that give us? Let me just get that there. That's a 33 away from that. That's going to be a 67. So that gives us 97.67, if I'm not mistaken. Yeah. Okay. That, look, let me just actually just sanity check that. Okay. So 98.33 minus 0.66 gives us a value of 97.67. Perfect. That the empirical rule tells us now that within one standard deviation, we should observe 68% of all observations. The vast majority of people should be within one standard deviation of the mean. Within two standard deviations, just do the calculations yourselves, take away 2 times each of these, take away 2 of them from that, add on 2 of them to that, okay? That we should have 98% of our observations, and that within 3 standard deviations of the mean, we should have 99.7% of our observations. Okay. So with this now, a company, so now when I have the standard deviation and the mean, yeah, when I add one of them on and take one away, I now have a lower bound and an upper bound for where 68% of the observations should reside, if that makes sense. Okay. And Lucas has mentioned here that all the values fall within 3 standard deviations from the mean. So there is no outliers on this sample of values. Are you correct? Well, it depends, Lucas, on what our metric is for determining what an outlier is. Okay. But yes, that would be a reasonable thing to assume. And that is one of the rules, yeah, is that within 3 standard deviations of the mean, if all of our observations are within 3 standard deviations of the mean, we would be saying that there would be no outliers. Another way to look for outliers, which is probably the more standard way, considering that this distribution isn't normal. Okay, this distribution isn't normal would be to take into, because the standard deviation within 3 standard deviations of the mean, Lucas, only works when the distribution is normally distributed, if that makes sense. Yeah. Okay. So in the case where we have skewness within the distribution, which in this situation, so I am really overcooking this now, Lucas, here, yeah, but just to get the point across, yeah, is that within this situation, the skewness is very small, yeah, it's minus 0.61, but there's still skewness there. As I said, we'd need to do a hypothesis test to test whether that's actually real or not, okay? But the point being is that because it's negatively skewed, okay, the mean and the standard deviation, the relationship between them doesn't hold anymore. Okay, it's now violated. Yeah, okay, because there's no symmetry. So what we'd actually have to do is we'd have to look at the quartiles. This is where the median. So now what we have, yeah. So maybe just to add this in here now. So now we have a look at the quartiles. So our quartiles and a quartile analysis. Okay, so we have. I'll do it from a box plot perspective. Okay, so let's say the distribution is normal. Okay, so and here's our scale: small values, large values. Okay, so here's the mean. Okay, here's the 25% mark. Okay, here's the 75% mark. So what we're saying here is this: is that here, and here. Here's the scale. So at this point and up to here, there's 50% of the observations. This is called the first quartile. The second quartile is the second quartile is the median. Okay, is the median, and then the third quartile here is the 75% mark. If it is symmetrical, well then we have these tails coming out, which is our least value and our maximum value. Okay, but the rule from a quartile perspective, there's 2 rules actually. An SPSS output define outliers when you do a box and whiskers plot as either circles or stars. Okay, and anything defined as a circle is an outlier, and any data value as a star is an extreme outlier. 1.5 times the interquartile range above the third quartile is values that are determined to be unusual values. 3 times above it, then we're talking, or is it 2.5 times above, we're talking about extreme values. So Lucas, yes, I do agree to your rule there within 3 standard deviations, but that'll only work for normal distribution. And in this case, we're really overcooking this question in order to get them 15 marks here. But hopefully that this particular analysis, yeah, of those descriptive statistics, was thorough enough for you to get a feeling of what you're trying to do when you're looking at the descriptives, yeah. The numerical descriptives are a numerical representation of this particular graphical descriptive that we have here, which is the histogram. Okay, guys, I'm happy enough with that now. Let's say, Yeah, Lucas, brilliant. That makes sense. Okay, no problem. Yeah, okay, that's great. So I think what I'll do now is I'm going to move on to the next question, which is question 2. And I'm just going to get rid of these here now. And now we're going to do some, I suppose we're going to do some hand calculations now. Okay. So I do apologize. There are 13 values here. 13 values ain't large, but from a hand calculation perspective, this can take a little bit of time to do. Okay. So, excuse me. So what we have now is we have another question, and it says that, so this is question 2. So question 2. Okay. And question 2 says that there's 13 high school students have completed a preparation program for taking the SAT test. So these have obviously been taken from an American textbook, yeah, right? So the SAT exams are American, but anyway, there's 13 high school, and then we have Fahrenheit over here, so you can sort of see where these have been taken from. So there's 13 high school students have completed a preparation program for taking the SAT test. Here are the SAT scores from the 13 students who completed the SAT prep program. So what I'm going to do is I'm just going to take them SAT scores, SAT scores, okay, and I'm actually going to just list them down here. So I've got 434, I've got 694, I have 457, I have 534, I have 720, I have 400, I have 484, I have 478, I have 610, I have 641, I have 425, I have 636, and I have 454. And this gives me a table, yeah, of scores. Okay, so there are my observations. Yeah, observations in all our formulas are symbolized by x. So an x is a specific observation, and here's the set of x values, the set of all observations. And what we need to do is we need to calculate the mean. So we need to calculate the mean, the median, and the range. Okay, we need to calculate the variance, and we need to calculate the standard deviation, okay, of this particular data set. Okay, now and then comment on our results. So I'm going to come back to the median. Okay. And the range is straightforward enough. Okay, we need to find the largest value in the data set and the smallest. Well, the largest value in the data set, just from a process perspective, let's just keep. I mean, this is overkill, but let's just keep this particular process, if that makes sense. And what we have is, let's find. Let me just move this across here so everybody see. So what I'm going to do is I'm going to find the largest value in my data set. Okay, 434 is the current largest. Well, 694 is bigger than what I had. Yeah, okay. So that's now my largest. Everything else so far. Oh, there's 720. That's now my largest. Yeah. 720 is the current largest. Is there anything else bigger than 720? No, there's not. So 720 now is my largest. My smallest value, well, 434 is my current smallest. Anything less than it? There's a 400. Anything less than that? There's nothing less than 400. So now I have 400 is my smallest value. So the range of the data set is 720 minus 400, which I suppose that gives us 320. So the SAT scores range between 320 values between the person that has the smallest SAT score, okay, or scored the least on the exam, compared to the person that scored the highest on the exam. Okay? So that's straightforward enough to do. Excuse me, it's the range of the data set. Now, to calculate the mean, there's a formula for the mean. Now, we're going to assume that this is sample data. So we're going to assume sample data, right? So the mean, and this isn't really, this doesn't make any difference for the mean or whether it's sample or population data, okay? But anyway, let's assume it's just from a symbol perspective. So now the x bar is the mean value. It's a symbol for the mean. It's equal to the sum of, when a raw data situation, it's the sum of all the observations divided by how many observations we have. Okay, this is the formula for it. Okay, now this technically is a frequency distribution, but the frequencies are all just one down here. Okay, it's not grouped, it's a discrete distribution that we have here. So to calculate the mean of this distribution, I need to add up all of these values. Now, I've done that already, right? But we could, I suppose, go through the pain of doing it, okay? We could take 434 and add on 694 and add on 457 and add on 534 and so on. But I've done that. This isn't really a tough calculation. Sigma x means go to the table, find a column called x and sum it up. So when we sum this up, what we actually get is 696. So 696. Oh, 6967 is the sum of those 13 observations. So x bar is now equal to 6967 divided by the number of observations, and there's 13 of them. So it's divided by 13. And when we do that calculation, so now we have 6967 divided by 13, that gives us a value of 535.92307. So let's say to 2 decimals. I'm going to round to the whole number. So that gives me 536 rounded to the whole number, because I don't want to be carrying decimals around with me in my calculation. Okay? So that's the mean value. Now, so this distribution now is centered on 546. And there's values that are less than it, you can see. Okay? There's values that are less than it, and there's values that are greater than it. Okay, so we can see that there's values that are greater than 546 as well. Okay, so there's values dispersed around it. And the question now that we have is, because there's values, let me just go to a new page here for a moment. Okay. So because there's values that are less than our mean, what did I say it was? It was 546. And you can see that there are observations. Let me just fix this page here. Okay, that there are observations that are less than it, okay, and so on. And there are a few observations that are bigger than it. But the important thing here is that every observation is a bit of a distance away from that particular mean value, okay? A bit of a distance away. And my question now is, if I had all them distances, which we can do, because you just take two values away from each other to calculate the distances. If I have all of those distances, what is the average distance? In other words, what is the average distance that observations are away from the mean value? And we define that to be the standard deviation. So the standard deviation formula looks like this. It says, take each observation away from its mean value. That's the distance now the observation is away from the mean. Square them. And there's a reason why we square, because the weight over here will be the same as the weight over here, or the momentum over here will be the same as momentum over here. But forget about that. And square them and sum them up. So in other words, sum up all these squared distances. So these are square distances. And divide by how many you have. And let's just modify that by taking one away, which is a complicated question of why we actually reduce that by 1. Okay, but that's because of the biasness and the unbiasedness of these measures. And I have a video on my YouTube channel that goes through that, why that's actually the case. But that this value, and I get the square root of this then, that this value here, S, is the standard deviation. Okay, it's the square root gets rid of the square. When we divide by n, it's big enough, it's just calculating an average. So what we now end up with is the average distance observations are away from the mean, which we call the standard deviation. So we have to do this calculation. And the variance, have we to calculate the variance? What's the variance? We have to calculate the variance. The variance is just before that, s squared. It's the sum of the x minus the x bar squared over n minus 1. It's the average squared distance observations are away from the mean value. And that's what we call the variance. So actually, we have to calculate that first. So we know what the denominators are in both cases. It's 13 minus 1, so it's 12. So the thing about we have to calculate is these sums of squares, yeah? So we need to calculate x minus x bar, right, for all observations. And then we need to square them. X minus x bar needs to be squared, okay? So we need to do that. Now, I've already done it, right? So what we've done is, let's just have a look at some examples here, okay? So I'm just going to move this over here, okay? So let's keep in mind that our x bar is equal to 536 rounded. So what we need to do is, for every observation, so the first observation is 434, I need to take away 546. And what we end up with, when we take 546 away from 434, we end up with a value of minus 102. So that's minus 102. Then the next one is 694 minus 536. See, the 536 doesn't change. The x bar remains the same. Okay, so, and we have to go through this pain of doing all of this. So that gives us 158. That's 158. And I've already done this, yeah? So we have all of these values now. So I have, the next one is minus 79. The next one is minus 2. The next one is 720 minus 536, okay? Gives us 184. We have minus 136. We have minus 52. We have minus 58. We have 74. We have 105. We have minus 111. We have 100. And we have minus 82. Each one of these values, Oh, sorry, I have a question here. Thanks, Lucas. In this case, is the population not the sample, right? Well, uh, in this situation here, look, this is a bit of a, there's not enough information to be given. There's not enough information given here to determine whether this is a sample or a population. But actually, when you think about SAT scores, yeah, SAT scores is more than 14 people take SAT scores, take the SAT test. So actually, if I want to use that argument, I'd be saying that this is a sample from all SAT test scores. Yeah, that makes sense. Yeah. So I could argue that this is a sample. I could also argue that actually this is just that class of students, that 14 students. Yeah, that makes sense. So hence it would be a population. But the important thing about statistics is that we're always using statistics to infer things about the population values. So if you're going to default anywhere, you should default back to assume that's actually sample data, if that makes sense. Yeah. And then we use the sample data to infer. Okay, brilliant, Lucas. Fair enough. Yeah, that's great. Yeah. So now let's have a look. Sorry, yeah, but Lucas, you are right. There is the question of, oh, am I dealing with sample data or am I dealing with population data? It shouldn't be ambiguous, to be honest with you. It's just the only reason that it's ambiguous is because these are exams. Yeah, in the real world, it's not ambiguous. Yeah, okay, you know whether you have a subset of a bigger group or whether you're interested in a bigger group or not. But it's just in case in these situations, yeah, it's a little bit ambiguous. But I think the argument would be that SAT scores that there's more than 14 students take them, and hence from that argument that these 14 students would be a sample from the bigger collection. Yeah. Okay. Just back to here. So really, what we have now is these x minus x bar values are the distance. Does that second row always equal 0? Does that second row? Which, okay, let me just see here. Sorry, Katie, you've got a question there, which says, does that second row always equal 0? X minus X bar. No, okay? It doesn't always equal 0. There is times when it would equal 0, is if the X value, don't forget, the X's are these observations, okay? The X's are these observations down here, Katie, yeah? Okay? The X bar is the average of the observations. So there, you could have a situation where someone's score is actually equal to the average, in which case their X minus the X bar would be 0. Okay? But you can see in this situation here, we've got 13 scores, yeah? The average is 546, and nobody in here has a score of 546. So you're never going to get a 0 in this case down this particular list here, if that makes sense, yeah? Because there's no 546s listed along here. Does that help out, Katie? So it is possible that X minus X bar is 0, but only in the situation where the observation, the X, is actually equal to the average of the group that we're measuring. Yeah. Okay. So it is possible, but you can see in this situation, none of them, okay, are equal to 0. Okay, because they're all different to the mean value. Yeah, some are smaller. You see the negative values. Some are to the left, and some are to the right. If that makes sense. But what we need to do is now we need to square them distances. So we need to multiply them by themselves. Sorry, I mean when you add them up, the sum at the end. Katie, yes, that's exactly right. Okay, you're right. You're right in what you're saying. So what Katie is saying here is this: is that we now have all of these distances. Okay, the negative ones are over here. You can see minus 102, minus 79, minus 2, minus 136, and the positive distances are over here. And what Katie has just said, which is 100% accurate, okay, is that one of the properties of this measure of center, okay, one of the properties of this measure of center is that the sum of the negative values will actually equal the sum of the positive values. And that's why we can't just calculate the sum of the x minus x bars and divide by n. Because actually, when you think about it, this is the natural way. This formula here is the natural. This is the average distance observations are away from the mean. Okay? So that's really what we want mathematically. We want this value here, this dispersion, this average dispersion. Okay? This average dispersion is what we're looking for. Okay, but because of this let's say property that the sum of the negative values is the same as the sum of the positive values, we can't actually calculate it. But what we do is we sidestep it, we square them, and then we come back to where we want to be through the square root to some sort of degree. So yes, Katie, I do agree. Carlos says to calculate the median, we have to put the numbers in order. Carlos, that's correct. To calculate the median in one way to calculate the median, yeah, would be to order the numbers. Yeah, actually, in most cases, it is to order the numbers. This is when we have discrete data, we order them and we triangulate in. But if I'm not mistaken, I did say that I was going to come back to the median calculation, as actually that's the simplest one to do. Yeah, in this situation, the rest takes a little bit of time to do the calculation. And so, yeah, Carlos, I do agree. Yeah, you do order them. Yeah, okay, but we're not dealing with that. We're actually calculating now the standard deviation and the variance. Yeah. So now what I need to do is I need to square them, and I'm just pulling across here what I've prepared already. So 100 negative times negative is always going to be positives, and positive times positives are positive. So this column here is always going to be positive values. So 102 squared gives me 10404. 158 squared gives me 24964. 6241. 2 squared is 4. 184 squared is 33856. 146 squared is 18496. 52 squared is 2704. 58 squared is 3364. Then we have 5476. We have 11025. Oh, 111 squared. Let me just get the calculator there. 111 multiplied by 111 gives me 12321. 12321. I've already done this, yeah. Or let's do it again. 111 squared, hit the square button, gives me 12321, which is what I had there. And then 100 squared is going to give us 10,000. And then we have 82 squared is going to be 6,724. Okay. But the point being is now what we have is the squared distance the observations are away from the mean value. Okay. And what we need for the variance is the sum of them. So we need to sum up this column here. And I've already done it. The sum of that column is 145579. Okay. So now we have it. So now we have, let me just maybe write this down here. Oh, let's just go across here. We got some more paper. Okay, here we are. So our formula now. I'm just going to get a little bit more paper, guys. I'm just running through this paper. Okay, so just bear with me here. Okay, so our formula, the sample variance, S squared, yeah, is the sum of the x minus the x bar squared divided by n minus 1. So in our case here, well, the sum of that column, the x minus x bar squared column, is 145579. So it's 145579, which needs to be divided by n minus 1, which is 13 minus 1, which is dividing it by 12. So when I do that, okay, so I have 145579 divided by 12 gives me a value of 1213. Let's just round 12132. That's rounded to the whole number. So on average, the square distance that observations are away from the mean is 12,132 SAT score points, yeah, which doesn't make any sense, yeah. But the standard deviation, okay, the standard deviation brings it back into sense. So S is equal to the sum of the x's minus the x bar squared divided by n minus 1. It's the square root of that, which is the square root of this value here. So we're introducing a little bit of error, 12132, because we rounded. So let's get the square root of 13132. So the square root of 12132 gives us a value of it's approximately equal to 110. Okay. Now what we have is this, and this is the interesting piece. Now I believe, yeah, is we have x bar is equal to 546. Okay, and we have s is equal to 110. So on average SAT scores are 546. But people are on average 110 SAT values above and below that, if that makes sense. Yeah. So now the empirical rule comes into play. If it was normally distributed, okay, we have within one standard deviation, we have, well, we're down to 426, and one standard deviation above is 646. And we'd expect to have 68% of people have SAT scores between them two values. Then we go out to 2 standard deviations and 3 standard deviations. So you can see the way this is working. That's if the data is not skewed. Okay. So guys, a lot done there. I think we've now done the mean, we've done the range, we've done the variance and the standard deviation. We have to do the median now. So Carlos, now we're doing the median calculation, yeah, which is we're going to take our data set. We're going to take our data set and we're going to order it from smallest to largest. Okay, so here's my data set. I'm just going to order it from smallest to largest. The smallest value is 400. So I'm going to write that down here, 400. The next smallest value in my data set, okay, seems to be, if I'm not mistaken, it's 425. Okay. The next smallest value in my data set, I think it's 434. Let's just sanity check that. Yep, it's 434. The next smallest value in my data set, okay, seems to be, if I'm not mistaken, it's 454. Okay. Then I have 457. Okay. So 457. Then I have 478. Okay. Okay. And then I have 484. Okay. Moving across here. Okay. So 484, followed by 534. So 534. Okay. Followed by, is it 610? 610. Okay. Followed by, okay, 636. Okay, I'll just put that there. Okay. Followed by 636, 641. So I'll just write that down there, 641. Followed by 694. Okay. Followed by 720. Okay, so you can see I'm starting running out of space here. Yeah, okay, it's got a little bit muddy over here, but the point being, I've ordered them from the smallest value in the data set, smallest, okay, all the way through to the largest value out here. Okay, so there's my smallest value, and here's my largest value. And the median value is the value that splits the data set up into two equal portions, where half the observations are less than it and half are greater than it. Well, it depends on whether we have an even or an odd number of values in the data set. But there's the same number of observations less as there is greater than. That's the best thing to do. But you can see the smallest and the largest value. So what we do is we triangulate in, we get rid of the smallest with the largest. So actually, any outliers are, see the way the median is going to immediately get rid of the outliers. Next smallest with the next largest, the next smallest with the next largest. And then we're triangulating in smallest with the largest, smallest with the largest, smallest with the largest, until we're left with either one or two values in the middle. In this case, it's one because there's an odd number of values in the data set. And this value here is the median value, because you can see now I have 1, 2, 3, 4, 5, 6 values less than it. We have 1, 2, 3, 4, 5, 6 values greater than it. Okay. If that wasn't there, let's just say that wasn't there, well, then the median value would be between these two values here. It'd be between them. So we add them together, 478 plus 534, and we divide by 2. It's what's halfway between them two distances, yeah, okay, would give us in that situation. So just doing both situations, although in this one, it is 484 in this example because there's an odd number of data values. There's a clear winner, okay? So that's actually that whole question done now, guys. That's question number, oh, where am I gone to? Just move this back around here. That's question number 2 completed. Excuse me for belching there. Guys, so I suppose my question now to you is, and you can always, this is being recorded here, so you can always reflect back on it yourselves. So I hope that this helped with that calculation. It's just that there's a lot of stuff to do in it, if that makes sense. Yeah. Okay. And that's where we currently are. Okay. Is that all right, guys? So hopefully that helped out there. So I'm just gonna move along now. We're an hour into this now. Yeah, that helped a lot. That's brilliant, Beatrice. Great stuff. So I'm just gonna move along. I just need to get some more paper here, just so that I don't run out of paper. That'd be disastrous. Yeah. Okay. So I have more paper here now. Okay. So now, question 3 and question 4. Look, question 3 is a bit of a mixed bag there in relation to this. It's to give this really any justice, I really need to go through all the probability rules and so on, yeah, and then to talk about permutations and combinations and things like that. But maybe I'll just do it as a solution, yeah, okay, rather than spending I have lots of videos up there in relation to probability, so maybe you can reflect over them on my YouTube channel. But this is question 3, so just doing them all in order. So question 3, right? And it says part A. It says a dice is rolled and a coin is tossed. So we dice, a dice is rolled, and a coin is tossed. Okay. So we have two things, two devices, yeah, two objects, yeah. Okay. And the question is, find the probability that the dice shows an odd number and the coin shows a head, yeah. So we have to find the probability, okay, that the dice shows an odd number, okay, and the coin shows what's the coin need to show? The coin shows a head. Yeah. Let me write this down as a mathematical notation. So what we need to find is, what's the probability, yeah, that the dice shows an odd number and the coin, C for the coin, shows a head. That's what I need to calculate, is that probability. And to calculate that probability, we need to know the sample space. Yeah, we need to know all possible things that could happen when we roll a dice and when we flip a coin. So you can actually see there's a set of ordered pairs here. So we have the sample space is going to look like this. Let's say we have the dice down here and the coin across. The dice, I'm assuming it's a 6-sided die. Doesn't have to be. Let's assume the face values are 1, 2, 3, 4, 5, and 6. Okay. The coin can be heads or tails. So now what we have is ordered pairs: 1 head, 1 tail, a 2 on the coin and a head on the a 2 on the die and a head on the coin, a 2 on the die and a tail on the coin, a 3 head, 3 tail, a 4 head, 4 tail, a 5 on the die and a head on the coin, a 5 and a tail, a 6 and a head, and a 6 and a tail. This is the sample space. Okay? These are the only things that can happen when we roll a die and we toss a coin. Okay? Well, the die the die could end up on an edge, yeah. Okay? The coin could end up on its edge, yeah? Okay. But let's just restrict it from them types of possibilities. Sorry, I have a few questions here. Carlos, to calculate the median, we have to put the numbers in order. Lucas, there is one last part about comments on the results. Oh, yeah. Sorry, that's got to do with the last question, yeah. Okay. Comments on the results. Well, to be honest with you, I'm at the calculate. We calculate the mean, the median, the variance, and the standard deviation. If you want to comment on them as an exercise, I suppose, yeah, I think you need to go back and have a look at what I did in relation to descriptive statistics here, yeah, because we took descriptive statistics; they were just numbers, yeah, okay, and we compared and we contrasted them relative to each other to give us an idea of the shape of the distribution. So what I would be looking at here is, if I want to contrast, maybe we'll do that here just so that we don't leave anything behind. Okay, sorry guys, I'm just gonna go back here. I didn't notice that question there. Okay. Lucas, yeah. So you can see the mean is 536, and also we actually calculated the median to be 484, yeah. So we have 536 and we have 484. So the mean is not the mean is 536 and the other one is 484, and the median is 484. So actually the mean is greater than the median. So hence this is positively skewed, yeah, because now we have the mean out here and we have the median here. The mean is attracted in the direction of the skewness. So even looking at that comparison, we have some relatively positive skewness in the distribution. Look, come here. Maybe what you need to do is you need to go back and have a look at the early part of the question, yeah, okay, which is the part 1. I went into a lot of detail on it, yeah. Just I am conscious of the time. I'm an hour into this now at this stage, yeah. Sorry, so hopefully, Lucas, not to fob you off there yet, but maybe just go back and have a look at that. Beatrice, thanks. Yeah, it helped. Brilliant. FXK, would points be given for answers using a calculator and not showing the workings? I think the lecturer is pretty clear on that particular point. Yeah, he says all calculations must be done manually with a full display of all steps taken. Yeah, so FXK, if I was to answer that, I'd be saying if you don't show the steps, you're not getting any marks. Yeah, okay. Because that's what he says. So let's play by the rules of the game, yeah. Lucas, perfect, brilliant. Frederic, Okay, awesome. Thanks, Frederic. Thanks, and keep her up. Okay, let me continue on here then. Yeah, right. So what we now have is question 3. We have a dice and a coin that are being dice has been rolled, the coin has been tossed, and we want to find the probability that the dice shows an odd number and the coin shows a head. Yeah, so here we go. So what we could do is this: is the probability of an event is equal to the number of favorable outcomes divided by the number of possible outcomes. If that makes sense, yeah. So just from ignoring that this is the multiplication rule, okay, just looking at it from this particular perspective here, okay, excuse me, what we have now is this: is that we have the number of favorable events is how many things are odd and heads, odds and heads, odds and heads. Yeah. So how many things are odds and heads? Well, there's an odd and a head, an odd and a head. There's odd and head. There's 3 odds and heads out of a total of 1, 2, 3, 4, 5, 6, 12 things. So the probability of that event, okay, is equal to 3/12, which is equal to, we have a 1 in 4 chance. Yeah. Okay? That's just diving straight into the sample space. Okay. But hang on. The dice and the coin are independent of each other. We'd assume. We assume that rolling the dice doesn't affect the outcome on the coin, and flipping the coin doesn't affect the outcome on the dice. So actually, this now, by a product rule, is actually the probability that the dice is odd times the probability that the coin is head. Okay? And actually, if you see that there, the probability that the dice gives you an odd number, well, how many odd numbers are there? There's 3 chances out of 6. Okay? And the probability that the coin is a head is a 1 in a 2 chance. Yeah. Okay? So what does that give us? Yeah. Well, 3/6 is 1 and 2. So that's 1 and 2 times 1/2 gives us 1 and 4. So also using the multiplication rule, okay, we get the same answer as going straight in to calculate the event. Okay. Look, guys, that's part A. I could spend all day talking about the probability rules. Yeah. But maybe I'll send you to the video. If you're around later on, I have got a live class running in theatre. I think it's theatre 2 at 5 o'clock. I can probably go into a little bit more detail there. Having a look at the next question, a 6-member group. Anytime you're creating committees and things like that, okay, they're always combinations. Yeah, so we have a 6-member group. So part B is a 6-member group. So the group 6-member group. See, there's no hard, fast technique for solving these particular problems yet, which is what's sad about it. Yeah, it's all experience and just things. So a 6-member group in which there should be exactly 3 women has to be created from 7 men and 4 women. Yeah. Okay. So in total, there's 7 men and there's 4 women. Okay. And the group needs to be that we want to create a 6-member group. Okay. But there needs to be 3 women. So we need 3 women. Okay. So no matter what, we need to select 3 women to 4. Yeah. Okay. So selecting 3 women, so we need to select 3 women from the 4. If that makes sense. And the way we do that is well, that's 4C3. Okay. The combinations formula, I'll just write it down. Yeah. So NCR, the number of ways of selecting all objects from n objects. Yeah. Okay. When the order, when combinations is what's important, is equal to n factorial all over r factorial times n minus r factorial. Okay. Where n is this number and r is this number here. Yeah. Okay. R is always going to be smaller than or equal to n. N is the total number of objects. R is how many things you want to take from the n. So in this case, we need to select 3 women from 4. So I have to calculate 4C3. So I could do it on the calculator. 4C3, I put in the 4, second function, the combinations button, which is above the 5 here, gives me a C and 3. So there's 4 ways of doing that. Okay? But let's see the formula. The formula says it should be 4 factorial divided by the order is 3 factorial times 4 minus 3 factorial. 4 factorial is simply 4 times 3 times 2 times 1. Divided by 3 factorial is 3 times 2 times 1. 4 minus 3 is 1, and 1 factorial is simply equal to 1. So you can see that these all cancel here with these, leaving us with 4 over 1, which gives us 4 as expected. There's 4 ways to select. There's 4 ways to select 3 women from the 4. Yeah. Okay. But hang on. The committee then has to have 3 women. It needs to be a 6-member committee. So the other 3 people must be men. Okay. So now the question is, how many ways can we select 3 men from 7? Yeah. So we have to select 3 men from from 7? Well, there's 7c, 3 ways of doing that, which is 7 factorial divided by 3 factorial times 7 minus 3 factorial, which is 7 factorial all over 3 factorial times 4 factorial, okay? Which gives us, it's 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1, because that's 3 factorial, times 4 factorial, which is 4 times 3 times 2 times 1. You see that they all cancel with that. The 3 times 2 gives us 6, goes with that. And what we're left with is 7 times 5 is 35 over 1. There's 35 ways of selecting 3 men from 7. So now we have that there's 35 ways of selecting the 3 men. There's 4 ways of selecting the 3 women. So there's 35 ways for the men. There's 4 ways for the women. So the committee now, each one of these ways for the men could be associated with the 4 ways for the women. So the total number is equal to 35 times 4, which gives us a value of, well, 35 times 4 gives us a value. There's 140. There's 140 ways to create a group of six people from 11, where the restriction is that 3 of them must be women, and hence 3 of them must be men, but that there's 4 women and 7 men in the group of 11 altogether. Okay, guys, to be honest with you, combinations and permutations, there's 7 or 8 rules, yeah, they're important, and they all build on top of each other. Okay, so I'm just doing that question there. I don't know whether it did any justice, yeah, but that's that question, and anyway, now nearly complete. The final part of the question here is part C. Is the blood groups of 200 people is distributed as follows, right? So we have 200 people, and their blood groups. So their group, right? Let's say the groups, yeah. Their blood groups are A, B, O, and AB. So the groups are A, B, O, and AB. Okay, and they're distributed as follows, yeah. So the frequency, the number of people in each group, yeah. So there's 50 people that have type A blood, 50. There's 65 that have type B blood. There's 70 that have type O blood, and there's 15 that have type AB blood. Yeah. So if you look at that, that should give us 200 in total. Okay? Which we have. What have we got here? We have 50. We have 100. What's that? That gives us 115, 130, and the 70 gives us 200. So everybody there's mutual exclusion across these groups here. Yeah. Okay. There's nothing shared. Yeah. Okay, by the looks of it, the totality comes to 200. So there's 200 people now, and we're going to randomly select from them. Yeah. So let's see. If a person from this group is selected at random, what is the probability that this person has O blood type? Explain your answer. Well, the probability that the person selected has O blood type is equal to the number of favorable over the number of possible. It's the ratio of how many people satisfy the condition to the total number of people. Yeah. So we have 70. It's equal to 70 over 200. Okay. And that's the answer. Okay? What's the blood group? Or the person selected has a blood group. Well, or is the addition rule. They're mutually exclusive. You're either in this group or this group. Okay. So hence we have it's the probability of X is equal to O blood plus the probability that X is equal to A, which is the sum of the individual probabilities, which is 70 over 200 plus how many A's are there? There's 50 out of 200, so it's 50 over 200, which gives us a totality of 120 choices out of 200. Yeah. And we can continue on to do all different possibilities here. Okay. Once again, I have videos up on these probabilities. I really wanted to get to this last question now, which is question 4. Okay. So guys, maybe I should just take a deep breath and just maybe ask, is everybody still with me? Okay. Because they're probably hanging on for this last question 4 here, which is the hypothesis test. And so maybe I'll just ask, is everybody good? 23 people there now. Brilliant, Beatrice. Okay, that's great. Yeah. Sean, thanks. Daniel, that's great. Katie, question 4 is not too bad because we did some of it in class. Excellent, right? Okay, brilliant. Irina, yes. Gabriel, yes. Excellent stuff. So everything seems to be good. Is there anybody that has any questions, or let's say anything that might be, let's say, still a little bit confusing? look, because I'm an hour and 15 minutes into it, yeah, I probably shouldn't have asked that question yet, because I'm probably just going to ask you to send me an email. Yeah, to be honest with you. Yeah. Okay. Well, anyway, let's have a look at question 4. Okay. So question 4. In this question, you will be using the data. So maybe I'll just bring this up here and hopefully you can see this. Yeah. So in this question, you will be using the data and results from question 1 above. Yeah. Assume that medical researchers are working on a drug to control body temperature at a mean of 98.6 degrees Fahrenheit. So actually 98.6 degrees Fahrenheit to 40 degrees Celsius, guys. Yeah, that's the recommended, well, not recommended body temperature. That's the average body temperature for humans. Yeah. Okay. Using the data from question 1, answer the following questions. A. Write a null and alternative hypothesis to test if the sample of 63 women's temperatures differs significantly from the target of 98. I think there's a typo there. I think that 98.7 should be 98.6. So look, I either use one or the other. I'm going to use 98.6 because 98.6 actually is the average body temperature. Yeah, it's 47 degrees. Yeah. Part A is to specify the null and alternative. Part B is to specify and justify an appropriate level of significance. Part C is to calculate a Z statistic and to determine if there is enough evidence to reject your null hypothesis. And part D is to report your result and fully explain your answer. Okay, so let's just get going on this. Yeah. So the null hypothesis, so our hypothesis, right, is, well, the question is, um, write a null and alternative hypothesis to test if the sample of 63 women's temperatures differs significantly from the target of 98. So we have a null, we have an alternative, and the question is there evidence to suggest that the average is different to 98.6 degrees? So is there evidence that the average is different to 98.6 degrees? So that's the alternative. That's what we're trying to show. So the null must be that it's equal to 98.6 degrees. Okay? So if you think about under the null position, the distribution, we're assuming normality, yet the distribution is positioned on 98.6. For me to reject this, which we assume to be true, so that's why I'm putting it there. So me to reject it, I need to find evidence out here or out here that's different. So this is actually a two-tail test. Yeah. So the significance now, that's the hypothesis. You can see actually that's one of our earlier hypotheses. Yeah. Okay. We said that there was 3 ways to define it. Okay. Let's see. So then part B is the significance of the test. Okay. Well, now significance is very subjective, but let's just keep in mind here that this is a medical research have produced a particular drug to control body temperatures. Body temperatures are very, very sensitive, things. For example, and I was just doing a little bit of research before I looked at this earlier, and actually hyperthermia is a body temperature of 40 degrees or more, 40 degrees Celsius or more, and hypothermia is 1 or 2 degrees below the actual average body temperature, okay. So you can actually see that within 2 or 3 degrees of the average 37 degrees of a body temperature, we have problems as humans. So you could end up killing people. So to be honest with you, the significance level of this test here, let's say if this was a critical piece, I want to know whether am I going to give these people, let's say, they're only going to go into surgery if their temperature is controlled. So how confident am I that this drug can control this temperature? So in which case, well, to be honest with you, I probably want to be my confidence, I want to probably be 99.999999, 1 in a million confidence, if that makes sense, or being prepared to be wrong 1 in a million times. But look, at this situation here, we're going to set alpha is equal to 0.01. Okay, I want to be 99% confident, confident in my decision. Okay. I would be saying that we need to be a lot more confident when we're dealing with drugs, and drugs going into people, and especially controlling body temperature. And probably the body temperature needs to be controlled before that person is admitted into surgery, if that makes sense, So I'm just going to set it at this, Now, otherwise, it just becomes a little too much to use to calculate when we're using our tables, Okay. It says calculate the Z statistic to determine if there is enough evidence. So our test statistic. Now, we're assuming that this is a large sample. Okay, 63 people is reasonable size sample. Just keep in mind that every single test that we undertake, we need to do a power analysis. The power analysis will determine the appropriate sample size. Yeah. Okay. But there's numbers that are bandied around 20, 30, and so on. To be honest with you, it depends on the type of the significance you're setting for the test. It depends on the type of power, the probability of that of observing something, if it's really there. All of these things, it depends on the effect that you're trying to observe as well. All them things have a part to play in relation to figuring the appropriate sample size. But I mean, in this case, he's saying to do a Z test. So the Z statistic is Z is equal to, it's X bar minus mu 0 all over sigma over the square root of n. Yeah. And I suppose in our situation, yeah, we're going to, because S is an unbiased estimator of sigma, we're going to substitute it in here. Yeah. So actually our test statistic is Z is X bar minus mu 0 over S over the square root of n. Yeah. That this is going to be our estimate of how far the evidence is, the X bar, away from the null position. The null position being 98.6. Yeah. Now, if we go back to our data, okay, which was provided in question 1, you can see the mean is 98.3. So we have X bar is 98.3, rounded to a single decimal. And the standard deviation, S, is equal to 0.66 to 2 decimals. Yeah. Okay. Actually, earlier on, I never talked about the standard error, which is actually this piece here, this S over the square root of n, but let's not worry about it. Okay. So now we have that the test statistic is equal to X bar, which is 98, minus the null position, which is 98.6, divided by S, which is 0.66, which needs to be divided by the square root of n, which is the square root of how many observations we have, and there's 63. N is 63. There was 63 women in the trial. So divided by the square root of 63, which gives us a test statistic. Let me do all of this. So we have 98.3 minus 98.6 gives us minus 0.3. I'm going to divide that by 0.66. And I'm going to multiply, invert and multiply by the square root of 63, which gives me a value of, it's minus 3.6078. So you can actually see, there you go. Was it earlier on? I'm just going to scroll back up here. Where have we gone to? Lucas, yeah. Earlier on, you talked about 3 standard deviations. Yeah, okay. So you can actually see now that we're actually 3 standard deviations below the mean value, the null position. Yeah. So we're well out there in the tail. Yeah. Okay. Which is loads of evidence to suggest that there actually is a difference. Yeah. Okay. So that's the test statistic done. So actually, from a distribution perspective, the null is positioned on 98.6, and the evidence is out here. Okay, the evidence is well out there. Okay, it's actually minus 3.6 standard units out in that direction. Yeah, so from a standard distribution perspective, that's positioned on 0. Our z is out in that particular direction out there. Okay, so where am I going to? I'm flying through this here, am I? Okay, so we have the hypothesis part A, we have the significance part B, and part C is the test statistic. So now part D is report your result. Okay? Oh, sorry, part C says calculate the Z statistic to determine if there's enough evidence to reject your null hypothesis. Okay, well, the null hypothesis, right? We need to calculate these critical values. Right? So our distribution, right, when we standardize, is positioned as 0. And it's a two-tail test, so we're going to put alpha over 2 over here, and we're going to put alpha over 2 over here, alpha being our significance. Okay, so we don't mind being over in this tail or over in this tail, and alpha over 2 is going to be half of this, which is equal to, so the area in the tail here, from here down, needs to be 0.005, and the area in the tail here needs to be 0.005. Okay. Now we've tables that allow you to, standard curve, we've tables that allow you to calculate that. Okay, but our tables are cumulative tables. They give you the cumulative area up to Z scores. Yeah, okay, so they give you the accumulation of the area. So just taking the right tail, you can see that the area that we need at this critical value here, and this critical C1 and C2, the area we need to its right is 0.005, which means the area to its left must be 0.9950. Yeah, that's the area to those. Now, my Z tables. How am I getting on here? Sorry, I'm going to come back down here. No other questions so far. So if I go to my Z tables now, These are National College of Ireland's tables that we've produced. Maybe ask your lecturer for a copy of them. Yeah, I've given loads to Eugene at the moment. I know Eugene, and Eugene's YouTube channel as well has great videos in there as well. So I'd recommend going in there as well to have a look at things. Yeah. So here's the Z tables here, right? And these are cumulative to give us the cumulative area. I know Eugene uses the set tables are a little bit different, and it's probably easier to use Eugene's tables than these ones. But we're looking, the area to the left needs to be 0.9950. So actually, I'm going to go to my tables, and I'm looking for 0.9950 in them, and I'm going to triangulate out to see what Z-score has that area to the left of it. And when I look at this here, I have 0.9950, 0.99. There we go. There's 0.9949. If you can see that, maybe you can't. Okay, that's a bad example here. Where am I gone? 0.9949 is under the column 0.07, and it's on the row 2.50. So it's 2.50. It's between 0.07 and 0.08. Okay? So the actual value that we're looking for is 2.57. It's between 2.57 and 2.58. So it's 2.575 is the critical value. So this critical value here is 2.575, which means this one through symmetry over here is minus 2.575. So now we can make our decision. Okay. So what we now have is this is we now know we have our critical value over here is minus 2.575. Okay. So, but we've observed data that's all the way out here. Our Z-score, okay, is equal to, what was Z-score? Our Z-score was minus 3.60. So it was minus 3.60, okay, which is in the tail. It's in the rejection region. It's so far away from where it should be. It should be here, okay, if there was no difference, yeah? Because if there's no difference between the evidence and our null, the numerator here is 0. Okay, if that makes sense. And what we found is that there actually is a difference, actually 3.7 units difference. So now what we're doing is we're actually rejecting the null. So we reject the null. We reject the H0 in favor of HA. And this is important now because now we can take the inferential step. Okay, this is the inferential statistics coming into play now. Okay, so now we can infer. So we're rejecting. We reject. Don't forget, we assume this to be true. We find evidence against this, so we're moving away, we're rejecting. And now we're making the inference, yeah, that the actual body temperature, that the actual average body temperature, yeah, of participants, yeah, okay, is different to this 98.6. It's different to it, yeah, because we've rejected. Okay. Report your result. So maybe if I was to do that, maybe an APA style, it might be something like this. Let's say a single sample Z test, yeah, so a single sample Z test, okay, was conducted, okay, to test if participants, okay, average blood temperature, was different to 98.6 degrees Fahrenheit. Okay, the results, okay, of the single sample test, okay, indicating that the average participant, okay, temperatures, blood temperatures, yeah, or body temperatures, isn't it? Body temperature, okay. The mean was equal to, well, what was our average? Our average was, it was 98, wasn't it? Was it 98.3? 98.3. And what was our standard deviation? We calculated that earlier. The standard deviation was actually equal to 0.66. 0.66. Okay? So the results of the single sample test indicating the average participant body temperature, yeah, was statistically significantly different to 98.6 degrees Fahrenheit. Okay, the T value, in this case, the Z value was equal to minus 3. Where's it gone? Minus 3.60. Okay, and the P is less than 0.0. 0.01. Okay, we don't know the exact p-value because we haven't done a p-value calculation here. But anyway, that's the result reported. Okay, in its entirety in APA style. Yeah. Okay. You need to report the actual average of your sample, okay, and the standard deviation, and then what that was being compared against, the null position, yeah, and then the actual magnitude of the evidence and the probability associated with observing that. Okay, guys, look, come here. It's coming up now to 16:29. It's nearly 16:30. It's probably a nice time to stop this particular stream here, an hour and a half. Yeah, I do hope that this was, um, as has had been mentioned. Katie mentioned that question 4 is not too bad because it was covered in class. So as has been mentioned, some of this stuff has been covered in class. I hope that my perspective and my angle here, I hope that this just helps you with your understanding. I hope it was intuitive, and more importantly, I hope that was helpful. And guys, thanks for tuning in there. Yeah, please maybe recommend this video to some of your colleagues in the class. Yeah, I know it is now. This is quite long. It's an hour and a half long. Yeah, but hopefully it will help. Yeah, thanks, Daniel. Brilliant. Thanks, Beatrice. Thanks, Lucas. Brilliant stuff. Right. Okay, I'm just going to end the stream there now. I think you can continue. Unless is there any questions? Okay, I'll go there. Yeah. Okay, I'm just going to end the stream now, guys. Okay, thanks for your time. Okay, no problem, Marina. No problem, Carlos. Okay, bye bye. No problem, Quiva. FXK. No problem.